Hello students, in this video we'll discuss homogeneous systems of linear equations. A homogeneous system of linear equations has the form, looks like this, looks like a11 x1 plus a1 n xn equals 0. All the way down to a m1 x1 plus all the way up to a mn xn is equal to 0. So here we have m equations and n variables over here. So we have m equations and n variables. And so let's make some notes about these things. So the first thing we're going to do is we can write this, of course, equivalently as an augmented matrix a11 through a1n, m1, of course, m1 through amn. We augment this with zeros, like so. And we can note, so note from these systems, this is one important observation. So here's our first note. Note that x1 equals x2 equals all the way down to xn. If they're all equal to 0, will be a solution to the system. Is a solution. And this implies that homogeneous systems are always consistent. Okay? So they're always consistent. Now, what I'd like to do is I'd like to figure out when there's non-trivial solutions. That's the next question for us. A question, when are there non-trivial solutions? Okay, and let's address this question, so answer. Let's suppose that m, a number of equations, is strictly less than the number of variables. So this says equations are less than variables. Then in this case, we let k be the rank, I'm going to call this matrix over here A, be the rank of A, the number of leading ones. Then, what do we know? Then we know that this implies that k is less than or equal to m. K is less than or equal to m, number of rows. And that says that m minus k is less than, strictly less than, n minus k. And this is greater than or equal to 0, which says that n minus k is at least 1 or more, right? So this says that n minus k is strictly bigger than 0. And this means that there are what? So n minus k are the number of parameters, right? That's the number of parameters. Okay? So the number of parameters in my system is strictly greater than 1, which means I have non-trivial solutions. Hence, number of parameters is greater than or equal to 1, means that there are non-trivial solutions. Great. Okay. The next thing we want to address is a very important thing which we're going to see later on in the course, and that's the idea of subspace, right? So here's a proposition, a little proposition for us. Prop. Let's suppose, let's call this over here star. Suppose that V and W are solutions to star. Okay? That, of course, means that A applied to V in our matrix notation is equal to the 0 vector, and A applied to W is a 0 vector. Then automatically what do we get? Then V plus W solves star, and lambda V solves star for every lambda in R, right? And of course, this just falls from the linearity of the operator V, and so the proof is trivial, right? The proof is just proof A of V plus W is A of V plus A of W. And that's the 0 vector, because this is the 0 vector and that's the 0 vector. And likewise, A of lambda times V is lambda A of V and that's also equal to the 0 vector because it's lambda times 0. And so what this shows that the solutions to this system form what's known as a subspace, and we're going to see that that subspace is exactly what's called the null space or the kernel of this matrix A, and we'll discuss the kernel or the null space of the matrix A in further videos. Thank you very much.